Today's lecture is on action potential. Action potential is basically the way in which an impulse travels down a neuron. That's what action potential is. Our last lecture we were talking about what happens in between two neurons and how they communicate one with another. But we're focusing on this lecture here. Here's our neuron. What kind of neuron is that? Multipolar. We're talking about what happens from here to here. Okay? That's what an action potential is. How transmissions go down from here to here. Like I said, we're going to spend pretty much this whole lecture period laying down the background information so that we can all be on the same page of how this is concerned. So I've got to take you way out of the picture to bring you back in. So let's start here. Background info. Number one, where there is a difference in electrical charge between two places, a potential exists. This potential is measured in what unit? Give you a hint. There's some batteries that are named after this. Like a type of battery named after this unit. Not brand so much. But like you got double A's, you got triple A's, you've got C, D, smoke detector, what do you have? I'll spot you a number. 9. Volt. There we go. In volts. Measured in volts. Okay? Let me give you a few examples here. Alright? In a 9-volt battery, we got this little rectangle looking deal. Same ones that are in my acoustic electric guitar. I've got these batteries in them, and sometimes they give out. In fact, I've got 2 of them. One on the back of the guitar and one in the wireless pack. And so to check it, you just take the battery out and stick your tongue on this. And if you get jolted, then it's still good. If you don't, then you need to replace it. Okay, not the best way, but it works. The reason that works is this, because one of these terminals is 9 volts. The other one is 0 volts. Therefore, the voltage, the difference in electrical potential between here and here, the difference in electricity, results in a potential of 9 volts. Okay? But the one in your car, let's get a little bit bigger on this battery. Okay? Unless you have a little car, then your battery's not that big. You got a truck, it's even bigger. You got a diesel, you got 2 huge batteries like this in there. One of them's negative, one of them's positive. Okay? One of these is 12 volts. You're like, well, how in the world does it start a car if it's not that much bigger than a 9-volt battery as far as voltage? It's not so much the volts that start the car as the amps. There's like hundreds and hundreds of amps of current that come out of this thing. If this is 12, guess what this one is?
0.
0. That's it. Therefore, there is a total voltage across these two that should be on or around 12 volts. Okay? Well, let's take it home for just a moment, where you plug your laptop and your phone in every night or all the time, depending on if your battery's failing. You've got this little dude here with this crazy smiley face. A little more, and this is pretend that's straight. This is and that this one's not bad also, but it is. Wow, everything about it's bad. All right. And now, yeah, they just look like two really sad faces. Why did you make me this way? All right. So these things right here, we're dealing with AC or alternating current, and this right here is the ground. Don't necessarily need it unless the appliance is ground, and that's because that's also 0 volts. One of these is a whopping 0 volts. You cannot guarantee which one it is, so don't like jam a paper clip in it. It could be either one of these things. One of them, nothing. The other one, it's got a little bit more. That is 110 volts. That's quite a bit more, okay? It's also why you have to have 2 prongs on all your appliances, because electricity goes into your appliance from here, through there, and then back out into the wall and grounds out into the panel and then into the ground for the house. So it goes in and out. Why am I telling you all of this?
There's our neurons work the same way.
Yes, that's precisely correct. Okay, so now we've established if you have a difference in charge, there is an electrical potential there between those two things that can be measured in volts. Because of the distribution of ions inside and outside of the neuron, an electrical potential exists. Now, I remember in physics 2 in college, my professor, he was very, very specific about terms, and very good physics teacher because he was careful about what he allowed us to say and what he didn't allow us to say. If we ever said voltage, we always followed it with the word across, because voltage is talking about the potential difference that exists between two places, so the voltage across those things. If we said current, we had to follow it with through, because current is something that travels through, just like the current of a river travels through. Okay? Now, here we're back. I'm going to bring this dude back here again. There he is. What kind of neuron was that again? Multipolar. We are going to take just this little section of this neuron here, and we're going to blow it up, okay? So here's a little magnifying lens, okay? And a plus, okay? That's what we're doing. And we are zooming in quite a bit, all right? So here's the inside of the cell, and here's the outside. Cytoplasm in here, interstitial fluid. So we're looking at a section of this tube, okay? So the axon is a tube, it's a vessel, it's filled with, cytoplasm, so on and so forth, okay? Now, what's on the inside? Well, we got a bunch of these things on the inside. Remember what those are? Those are proteins, and walk away like... That's it, okay? These proteins, ladies and gents, are negatively charged. Now, again, this is not to scale. I just want to show you. In fact, none of these things are going to be to scale because the size would be pretty jacked. So we have, so let's make some notes here. Negatively charged proteins on the inside of the cell. Okay. All right, that's already going to start the ball rolling. Negatively charged proteins on the inside of the cell. That if you have these colors, I would prefer it, but I'm not going to be a tyrant over your notes and how you handle stuff. But if you have blue and orange, that would be awesome for the next few things that we're going to do. So I'm going to draw some ions here. Na 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 na. Na 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 na. Hey, 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 sodium. There it is. Here's a bunch of sodium ions. Positively charged sodium ions. And I like blue for sodium. Now, is sodium actually blue? No. It's a metal that cuts like butter. In an ionic form, it just tastes salty. Okay? But that's neither here nor there. But we're going to make a note here. There are positively charged sodium ions on the outside of the cell. Then we're going to have these dudes on the inside. They have the same charge as sodium, just 1 plus. Any guesses who this might be? Hydrogen would be a great guess because it would fit, but not in this case. If it were hydrogen, we'd have an acid here, and that'd be bad for our nerves.
Potassium.
What's that?
Potassium.
Yes, indeed. These are potassium ions, K plus ions. And that's what I want to do orange here. When we do this illustration in lab, we're going to use blue and orange gumballs for it. It's not really a lab, it's more of a demo, but okay. Positively charged potassium ions are inside the cell. Okay, this is at rest. At rest, this is what it looks like. Well, you're like, there's positive inside and positive outside. Doesn't that just average out? It would, were it not for these negatively charged proteins. Now, just like we were talking about with our 9-volt battery friends up here and our various other things, there is one place, there is another place, and the difference between those two results in voltage. Here are the two places. Are you ready? Inside the cell and outside of the cell. There is a difference in charge that exists between these two places. Okay? Therefore, there is an electrical potential. That potential is known as transmembrane potential. Now, it's measured, and the unit is volts, but folks, it would take so much energy if all of our nervous system had to use full volts to do their job. You could never eat enough for your brain to function, okay? So we're going to function in thousandths of a volt. What would we call thousandths of a meter? Millimeters. So what are thousandths of a volt? Millivolts, okay? So the transmembrane potential is measured in millivolts, little m, big V. Now I'm going to put a number in front of there. The number here, the one at rest, the one that really matters for this, is minus 70. Minus 70 is the quantity, is the resting membrane potential, okay? So put in parentheses, at rest. This number is going to change a lot, but I'm not really super concerned that you know how and which way it changes just yet. This is just the background information. I'm telling you what this looks like at rest and why it's getting ready to do something. Question? Oh, yes, I'm sorry. Here we go. So positively charged sodium ions, positively charged potassium ions. Sodium on the outside, potassium on the inside. That should beg the question, how in the world do they get there? Naturally, they wouldn't necessarily be there on their own, so what in the world? What's the deal here? Let me tell you, okay? All right, so I'm going to start at the top here. You might be at the top of a new page, but if not, that's okay too. Okay. Three. Sodium ions are outside, and potassium ions are inside the neuron because they are pumped there. By, and this is a great name, ready? Sodium potassium pumps. They're pumped there by sodium potassium pumps. That's what keeps them in play. That's what puts everything back to normal. All right? So now we're going to zoom in even further. What we're looking at, folks, what we're going to draw here is a zoomed in version of this line. What does that line actually represent?
The edge of the axon.
Yeah. What do we call the edge or the boundary of all cells? The membrane. Right. Now some of them have walls, but we don't. All animals don't have walls surrounding our cells. Now, if you recall back to biology, what we've got here in the membrane we've got two layers going back to back, yeah. Phospholipid bilayer. Okay. But within the phospholipid bilayer, which is what most of the cell membrane is made of, so let's label this neural cell membrane. That's the neural cell membrane. Like every other cell membrane, it's mostly phospholipids. Thank you. And so, but included and adjacent to these phospholipids, we're going to find different proteins, okay? Again, we keep coming back to proteins. The sodium-potassium pump is one great example of proteins. And just to make sure that we don't forget this association, I'm going to draw it in here like that. Proteins, most of the proteins in your cell's membranes are basically just gates. They will either allow things in or out. And this one is a little more complicated. It doesn't allow things in or out. It forces them one way or the other. Okay. Sodium potassium pump. That's this guy. Okay? Now, again, scale's going to be way off here, but I'm just going to draw what do my blue dots represent? Sodium ions, and my orange dots represent potassium, right? They don't start out this way. Something's always messing them up, and they don't stay that way for very long. In fact, I'm going to throw one of these dudes out there. I'm going to put one of these guys in here. And what happens is this. Sodium potassium pumps sodium out and pumps potassium back in. That's its job, is to pump these things and put them where they go. All right. Now, it's expensive. How is it expensive? It takes energy. Energy in the form of what?
ATP.
Yes, indeed. Okay. These pumps are fueled by ATP. It requires energy. Energy is required to send ions, this is important, ions from low concentration to high concentration. There's already a lot of ions out here. There's already a lot of sodium ions out here. It doesn't naturally want to go that way. So it takes energy to pump them in. Or out. Do you remember the percentage that you heard the other day? Though your brain only takes up about, or makes up about 2% of the body's mass, it takes up how much of its energy? 25%. Okay? 25% of the body's energy is consumed by the brain. Here's where it goes. That energy goes into resetting the sodium and potassium, putting them into the right spot. That is the most expensive thing in the brain, and probably the most expensive thing in the body as far as processes are concerned. Is that energy in your brain goes to sodium-potassium pumps, putting sodium back on the outside and potassium back on the inside. Well, why, Mr. Helling? For reasons I'm going to explain tomorrow. Okay? Sodium is pumped out while potassium is pumped in. It's not exactly a one-for-one exchange, but these pumps do both because it makes sense. They're needing to reset the other way, so like this one pump does both. It sends one out while taking some in. Okay? Now, quantity. So we're not confused that it's not just that one dude. Here's our multipolar neuron again. Okay? He's doing his thing. Here's where they are. I'm going to connect them here. They're here. These pumps are all along the axon. And it's not just like one or two of them. There's thousands and thousands and thousands of these things in every neuron. And it's not just like one in this section. This section is a tube, and the tube is surrounded by these things. They're all working. That's why nervous tissue is so expensive. To be able to do its job, it has to constantly be reset. Okay. 2 more big ideas, and we'll call it a day. All right. 4. In addition to pumps, there are proteins called ion channels that open or close to allow or stop diffusion of ions. Okay? To allow or stop diffusion of ions. This is always going to be from high to low concentration. Concentration sometimes illustrated by brackets. Okay? These channels are specific to sodium or potassium. So there's going to be one that allows potassium to get through. Okay. And there's going to be one that allows for sodium to get through. And they can't pump. They're only allowing things to go where they're naturally going to go, from high to low concentration. All right, last concept is dealing with these things I just talked about. Number 5. There are 3 types of ion channels. Defined by what opens them, what opens or closes them. Okay. This is our last thing for the notes. So, there are these sodium channels and potassium channels, and they're basically going to be activated by one of these 3 things. The first of these 3 things is this: chemicals. So there are chemically regulated ion channels. These will open or close in response to chemicals binding. So the chemical will bind to this ion channel, and it will either open it or close it. Can I bump somebody's notes from Tuesday? Somebody nearby? Notes from Tuesday? Let me show you where you're going to find one of these. Okay? Where you find a chemically gated, a regulated ion channel is right here. Those receptors that are at the synapse, that's what they are, is chemically regulated ion channels. Chemicals bind and it causes them to open or close. Okay? So that's where you'll find those, is primarily, thank you, at the synapse. Okay? The second one is by far the most common. I don't know for a fact, but I'd be comfortable saying 90% or more of all the ion channels are this next one. They're voltage regulated ion channels. Open or close in response to changes in voltage. And voltage, this case being transmembrane potential. When something changes there, they'll open or close. That's how most of them operate. That's how most of the information is sent through your nervous system. It's through these guys. It's as a result of these guys opening and closing. The last one here is handy to you right now, so you can sense how much pressure your fingertips are holding your pen with, and it's this: mechanically regulated ion channel. These open or close in response to physical distortion. That would write senses here. For the fact that you can feel temperature in the room, It's because these things are responding based on those changes in temperature, or that temperature, or the pressure, or pain, or these types of things you feel as a result of these things opening and closing in response to the pressure or something physically changing them. So those are all the types of ion channels. We are just about done with the background information that you need to get started on action potential.